Hi, my name is Abia. I'm from the Center for Transportation Equity Decisions in Dollars, CTED. We're here today with our CTED webinars. Before I begin to introduce our lecturer, I would like for anyone to maybe type. There's a typing option up there where you can ask questions and things like that, then you can hear me. Okay, great. All right. So thank you for joining us today. Today's webinar is on fast reference-free acoustic crack measurement, which Dr. Suyun Ham, who I'm going to introduce shortly, will explain more to you about. It's a system and where he's testing in transportation infrastructures using non-contact ultrasound. A little bit technical, but Dr. Ham will shortly explain what all of that means. A little bit of background. So Dr. Suyun Ham is an assistant professor at the Department of Civil Engineering at UTA, which is the University of Texas at Arlington. He was a postdoctoral research fellow at the University of Nebraska at Lincoln after he obtained a PhD degree at the University of Illinois at Urbana-Champaign. Before that, he worked in industries for 7 years as a researcher and a structural engineer on projects including buildings and other infrastructures. His primary research is non-destructive evaluating, imaging, and sensing, where he applies mechanical field phenomena to assess the condition of infrastructure materials and structures. He deployed the technology using a robotic scanning system, and special topic is integrated damage assessment for concrete structures with a fully contactless ultrasonic scanning system. He applied this method to laboratory samples and field testing, such as nuclear power plants, bridge decks, and deteriorated concrete rail ties. Dr. Ham is a committee member of the ASCE, Structural Identification of Constructed Systems. He was the recipient of the American Society of Non-Destructive Testing Fellowship Award in 2012. So thank you, Dr. Ham, for joining us.
Thank you.
And he will now take over the presentation. So here you go.
All right, so welcome everybody. I'm Suyun Ham, University of Illinois. I'm from the PhD. I'm also professor in the University of Texas, Arlington. So I'm so excited today to introduce our current CTEDD projects. So basically, today the webinar is final presentation for our CTEDD project. So we have a 4 section today. Section 2, 3, 4 is mainly the project, the contents that we are doing for CTEDD. And then the section number 1 is the little bit about background that how we can choose this topic and what the problem and motivation, etc. So these are all our today's presentation here. So I'm going to start now. So basically, most people familiar with this ASC reports that infrastructure these days, the infrastructure agency shifted from the efforts from the building new structures to assess the or rehabilitating the structure. So that means maintenance issue. So that it's a great opportunity to we are focused on the infrastructure assessment. And so that's why we are most of our project is the NDT project. So for those who are not familiar with NDT technology here, so that my class, NDT class, I introduced this little bit background of NDT. What is NDT? So many people see NDE, NDT, or NDI. These are all same concept here, which is looking at the damage or deterioration without damaging material, like we did for hospital. At the hospital, we are looking at the problem here. So look at the sonogram from my 8-year-old boy, and took X-ray, or some people use MRI for the human body. So instead of the human body, we are looking at the inside the infrastructure deterioration that technology. So like at the hospital that people use blood testing. So there's a lot of drug destructive testing method here that 20 years ago I involved the consulting company that usually have some coring and destruct testing as well. And then also we have non-destruct testing for infrastructure, so that we are investigate like X-ray or MRI. So we investigate here. So these are our goal from our laboratories, that we are using some advanced inspection technology and then find some deterioration, and using the information technology, we share all the data and communicate with other stakeholder, or we can collaborate with other research as well. So these are our goal, and also this project and my expertise focused, fit in the three focus area from CTEDD 256, and for example, we are doing some maintenance to transportation infrastructure, and also we're using some remote sensing system and information technology that I will show you today. And there's many topics fitting into this three focus area, so that I'll address those topics as well. And also, it's important these days that current project I have these days, looking at the deterioration or evaluate the payment or breach, because the stakeholder needed to now right time, because we don't want to overestimate or underestimate the payment evaluation or breach. Then you lost $1 billion, not $1 million, this $1 billion loss. So to avoid kind of economic loss, that we need the right time assessment to do this. This is kind of initial motivation to do it. So what kind of damage that we're interested in these days? So these are kind of payment evaluation for delamination bridge tag. So most of the damage, the issue from the bridge tag is delamination. So this is kind of result from the delamination that caused by the corrosion, mainly rebar. So look at this here pothole or many kind of damage out there. But most of the case that we see here, hidden crack, which is called delamination, horizontal crack. Again, this is caused by the corrosion. So that if you look at this inside the crack, that many technology try to do from some image processing, the other technology, but it's not able to see the inside in this delamination. So this is a kind of impact that innovative technology, how we can inspect such hidden crack challenge. And then the lamination is the most critical problem in the bridge tag anyway. And then a lot of other macro or micro cracks on the transportation infrastructure, for example, crack caused by the external load, vibration, and also we have some chemical attack from the ASL freezing thawing. So for example, the Illinois, and there are a lot of freezing thawing problem in the Texas has ASL and other salt scaling problem. So that most time when I teach the PhD course, that deterioration class, I call this a Fantastic Four, like a Marvel character, because they are really teamwork, then they kill the infrastructure anytime. So these are kind of a very good example of the ASL crack. But of course, we don't want to find this kind of last stage that, like, you don't want to find the tumor last stage that is too late, that replace time. So we want to find the early stage that you can fix it, or we have a new strategy, or you can change the policy that we can help this our society infrastructure. So again, so many people say the micro crack is not really significant impact on the structural performance. Yes, that's true. However, if you look at here, that this deterioration cycle continues to progress, like say Fantastic Four, they have a teamwork, and then they have boosting. For example, if you have a crack from initial micro crack, and it allowed the chloride chemical, so that this chloride ion is boosting your corrosion, and then you have large delamination, and this delamination caused a pothole or vertical crack, and it's more crack, and then it has getting worse. So, like I said, like if you want to find the early stage tumor, so we wanted to help something to find the early degradation, then we can help, because you don't want to lose $1 billion wrong replacement, or you want to too late, you have to do more, you spend more time. So that's why most of my project in here and other stage DOT experience that they really need to find the accurate maintenance data so that we can help. So what's your current technology doing so far? So we have a very, this is like called the chain drag impact. So what happened here, this is one of the correctly defined ND technology, which is the defined delamination chain drag. And these methods, this looks like an inefficient way, but this is only way in state practice to find this damage here. Of course, many people also try to use the other advanced technology, but that's very slow. And then this is still, believe it or not, is popular and common method in DOT people area. So these kind of challenges, for example, if you want to look at the billions number of the concrete cross-tie or rail, or you have a large infrastructure, and if not repeatable, not sensitive, also not fast, then somehow you wanted to using some fast scanning system, like maybe like MRI system, or then you can find, also you need some very sensitive method to find the crack anyway. Or somehow we have, you want to kind of profile with some rapid scanning system so that you don't want it to close lane, you don't want it to miss any kind of crack, so that you can maintain, if you close lane, that you have also economic loss anyway. So you don't want to overestimate or underestimate, also you don't want to close lane anyway. So these are kind of a motivation. We invented the one-side air couple, which is non-contact system to develop. So these are, I'm going to spend 5 to 10 minutes, a little bit about background why we choose the CTEDD technology, that is project here at RACM. So this is the motivation, is this extended my NSF project. So how we can get this NSF project, and what's the topic that we extend, and what's the research gap still we have to do this. So this is the NSF project, it's a very, very deep understanding research project, but the CTEDD is more like connected this research academic area to the stakeholder to use this technology. So I'm going to spend 5 minutes about what is the content of our previous NSF project and why we continue to study. Okay? So basically the two reasons we got this NSF project is the time we write a proposal, there's no technology to do non-contact system. As I explained that, you need a non-contact system, otherwise you don't want to contact the sensor every time you want to evaluate the entire system. Of course, many people use image processing and other non-contact system, but that's only focused on the outside feature, not inside the one. And the inside the one is impossible. So that's why the reason the reviewer, why we choose this proposal, because this is very innovative technology that is non-contact system fashion, which means we are sending the mechanical wave without touching anything, that we can evaluate the inside the concrete or pavement evaluation. So a lot of things I want to skip this one, but I just show you that how we can do it. And then in our UTA, we also develop all the sensor, manufacture all the sensor as well here. So another reason that we are the NSF, we got this NSF is the, although we have a non-contact action, that we needed to kind of advanced and then reliable the crack measuring system. For example, a lot of many NDE technique, you need a reference technique, which means you don't know, let's say many field area, there are a lot of unknown case, because if you get the value, is that really true damage index, or is that really true crack volume? So we really needed some kind of reference data, so that without any reference, if you just get the value, that, oh, this is something that values indicate maybe severe damage or not. So that's why we wanted to develop this one. For example, there are a lot of the damages type here, although all the damage type here, I invoke the project from the DOT, different DOT project, but let's focus on the micro crack or macro crack or distributed crack. So if you look at this crazy inhomogeneous medium, let's say we have a random crack. I'm not going to explain all the mathematical equation, and I just roughly here. But if you look at this, let's say this this gray color is, let's say, crack, like a little micro crack. I mean, we can detect the macro crack, but the micro crack is challenging because we wanted to find all the damaged states. So usually we use a low frequency, which means large wavelengths. Think about your bread flour sieve. If you have a large size of the bread flour sieve, you can easily filter all this flour. But at the same time, you cannot detect fine flour. Same thing, if you want to use like a high frequency, which is low wavelength, you cannot actually even propagate any mechanical wave through the concrete. It just goes away and scatter a lot. So we have to use large wavelengths. And I want to scan this like a small crack. That doesn't make sense. Sounds like it doesn't make sense, and they contradict. Like diet chocolate cake. You know, people believe diet chocolate cake is not working, but this proposal is effective diet chocolate cake. So anyway, people, I mean, you don't have to remember all of them. You can remember just effect diet chocolate cake. So these are proposal. I never use the diet chocolate cake in my proposal, but this is a good parable for steps. Anyways, so all you can remember here is it looks like physically impossible, but we can extract any kind of crack regardless of the aggregate type or concrete, whatever homogeneous medium. You can extract the crack from the infrastructure system. So let me skip all the mathematical equation, but this is a part of my NSF project, and less than by 3 minutes, I'm going to finish my preliminary result. Then I will start with our main CTEDD project. So before I start the CTEDD, we do have many kind of using RACM technology. We do some FEM simulation and synthetic damage crack, and also we have a lot of laboratory experiment here. The whole point is like a numerical or laboratory testing and some real ASR crack sample here. All the result was good, and which is that we have a very lower damage level, not the severe level, than other entity cannot detect this crack, but we can detect this crack and extract the volume. That's the conclusion. And also we can scan the entire slab, then we can see you can see the color indicated crack volume. So the red color indicates more crack, and you can see like the 0 day. And if you deteriorate more, you can see popped out everything, and then you can see more damage show here. So this is a really good application. Stakeholder, remember that we can use this technology for bridge deck or the pavement. So you can see all the time history that how this crack is developed. And we can also help this data to other people, for example, planning people or strategy people. They can use that for the time history, like a prediction and other technology in other systems. So anyway, so this is a motivation that we hear. So although we successfully finished our NSF project, so I have a lot of there are some several questions I have from this project. So I want to kind of share this technology that everybody can use this technology. Then and then also all the technology is not perfect. We have to still improve it, but how we can improve? Well, of course that it's difficult to for example, what about another question that, what about the aggregate effect? How you can handle this aggregate effect? So this technology or conclusion is, regardless aggregate type, you still get the crack, but still have lots of question about different type of aggregate so we have to develop some advanced modeling so that people can still continue to study this one. And also, conclusion of this project was we can extract the crack volume, but how we accurately extract the volume, or can we trust all the time? There are lots of verification needed. And also, although this system is great and not, other NDT techniques not compatible, but still, this is, as you can see, remember all the estimated equation is so difficult to understand. So, difficult to communicate with stakeholder and difficult to communicate with other engineer, so this is kind of a whole question. So that's why this is motivation to write the CTEDD project. So for that answer, that we will do some advanced modeling and large scale real sample with the multiple verification process. And the last stage is that the real-time GIS mapping application, so that everybody can see the technology and see the result in daily base. We can see all the data. So these are kind of three main topics for CTEDD. So this is kind of our vision before we do the project, so that this is our purpose, that we can scan and inspect all the damage data, collect data, then we can analyze, and all the information go through the app or web-based program, so everybody can see all the results and easily access. Okay, so as I mentioned here, we have a three topic, FE new modeling, and then large scale, and then real damage sample testing. And also we have a real-time GIS and mapping system. So that's the whole things. And for performing this project, I have 3 PhD students and 5 MS students involved in this project, a lot of tasks here, and then all my PhD students really did a good job, so that I really appreciate, first of all. And then we finished all those tasks anyway, and then each breakdown with the 5 tasks that we did. So first task was we developed the advanced FE modeling, and before we talk about it, we wanted to kind of understand our RACM method, that how this affects, so that so our lab has a lot of questions to understand this method beyond our NSF. Then we wanted to kind of find some aggregate effects. So we was seeking for kind of aggregate modeling, how we can, because realistically, that if you want to cast the concrete, you cannot control the shape of the aggregate location, then it's impossible to compare each other. So that's why this is called motivation. We developed the aggregate model, because I'm going to skip all the kind of detailed literature review, but even current 2018 project, most of the people focus on how we can image with iPhone or camera, how you can make digitalized image from the actual real set, but aggregate, but that's not our purpose. We wanted to generate randomly, but that has to be close to realistic aggregate shape. And then many morphology-based paper, we try to use this equation, and none of the equation is not close to real aggregate sample, so that that's why we decided to develop our own code, so that we can simulate realistic shape. And then, so what we can do, this is very practical actually. And so what we do is, we slice all the sample, take a picture, and then we can digitalize all the image. Then we have more than 1,000 aggregate profile, and we check the similarity, and then we make all the profile of each aggregate. And then after we profile aggregate, and then collect all of them, and then we made a function, shape function for each of the category. But before we do that, we have a lot of statistical testing, statistical analysis, that we categorize of the needle crush round, because the previous all the technology, that we cannot create all 3 shape easily. That's the problem. So anyway, so you don't have to remember or understand here, but we have a lot of step here that we skip here, but the whole point is, once you have this red equation, the science, and this table, which is collecting from the 1,000 aggregate, then you can generate billions different shapes here. That's the beauty of part. So whoever, you don't have to understand the morphology study, because these all the generate formula and this table can generate realistic shape of the aggregate, and so that everybody can use it. So this is kind of the whole point that here, and then we have a 3 category of the needle shape and round and needle and crush aggregate shape. So we can create all aggregate. So we already verified, we will skip this one, but basically what I did here, we have image from the model from directly from the imaging, and then we have used our own codes, random generate, but same category. But also we also compare with the other aggregate shape from the other researcher, so we compare it. So basically what we did here, if you look at the reference aggregate or CCT, these two is this is from the actual image, then this is for what we from our code. So whenever you use the table and this equation, it's fitting within this actual image. So we verify many steps here. So if you have any question, let me know. I can explain more detail. But this time, whole point is our model is actually very close to our actual image of aggregate. So you can use this kind of aggregate modeling for many kind of here. So for example, many DOT people is interested in also soil compaction and foundation, and they're interested in like aggregate shape and aggregate modeling, and also compressed testing. And so we can use many kind of, like for example, we can use for prediction of the soil aggregate stability or material characterization, foundation. So this technique can use the other area as well. So I hope many people can use this technology. So after this modeling, that we understand this method, that we wanted, the last 2 stages, we test the real damage sample, and then we also have mobile app development. So first thing that although we have many laboratory testing, but still we have a lot of questions that how about the different damage type, for example, sewing or ASR, or how about the other damage? How this RACM's technology can sensitively measure the crack, and how we can extract the volume correctly. So we need some further verification with other NDE technology or the laboratory testing, and before we go field test. So the left side one is the ASTM standard 50,000 K, C50K, the expensive equipment for ASL sampling. What that means that you're during the day you're doing cold, freezing temperature and hot temperature, freezing temperature, so that inside the concrete is expanded because of the different volume depending on the temperature. The problem here is a very small sample. You can get all this standard size, and if you want to test on the largest lab, it's impossible. So we was looking for like environmental chamber, but no one can do that for freezing sewing for large sample. So that's why we develop our own environmental chamber. And then conclusion for this environmental chamber, we call large size freezing sewing machine. It's good for other application. For example, maybe winter time, how the crack is propagate or other temperature effect. So we can use many other applications, for this machine. So anyway, so these are just all the configuration that we developed this system. We have a control system, and we'll just roughly skip this page. And basically what happened here, that we have a freezing and thawing cycle for every time, every day. So we can make a damage sample that we can have some real damage sample here. So Before we have crack testing here, so I'm going to introduce a couple of methods. So this is our non-contact RACM method, and the left side is the traditional vibrations called resonance testing. What happened here, this is very traditional but very reliable, but only for small sample. You cannot test for on the large scale or field test because it's only for small sample. But it's really good. So if your target is vibration testing result, it's fantastic because our technique can do any size. That's why we can invent monitoring the infrastructure system. And also we use some 3D tomography. Each contact slow, but it's good technology to compare. So the first step what we do is we measure the extension meter data. What happened here, when you have a crack, think about that. When you put in you fill the fill the water in the container, then put it in the freezer. Sometimes you have a crack because you inside the volumes increase. So same thing. So if you have an internal distributed crack by the ASR when putting sawing, you see the structures and volumes increase. So we measure with the very sensitive extension meter measurement that we can. This is for reference data we compare. So anyway, so the whole point is that you have a vibration test, but you can look at that this vibration test is not accurate as how you as the damage goes or high level damage. You see the problem here you cannot detect. But while our RACM can increase, the increase means you have a more than crack volume so that you can see they're able to see the crack development here. So these are just roughly I can show you that our system works. And you can use many other applications that if you're interested, so you can monitor other deterioration, you can, or sometimes the CD replace a new material that maybe they have a shrinkage or dry shrinkage or initial crack. So we can keep monitoring because you can scan entire pavement quickly so that we can use this technology for soil compaction. Maybe they see if they have a foundation problem. We can use this scan machine to see if there's any void volume so we can extract the volume. So you can use this technology in other applications. So if you have interesting foundation area or soil, let me know if I can. Okay, so finally we have a last stage here. So although this RACM is effectively find out this crack volume, but still it's so difficult, many complex equation and difficult algorithms. So our idea is that how we can share this data, how we can communicate, or how they can easily access here. So that's what this is motivation we developed the system. For example, here, this is a design sketch that we developed Android app, so everybody can download the quality SMTL APK. And this is a design sketch that I mentioned already that we have some damage sample that you can access anytime, and you can choose the different NDE method that how you can compare each other. And day by day, maybe February 2nd, February 3rd, we can always look at all the data. Not only the field laboratory data, you can search all the field data. You can easily, what's going on. For example, you can choose the app here, and then you can choose the location that you popped up all the information. So you can choose any. So this is the kind of introduction that instruction is that you can use this application. So let's look at this one. So we have a couple of field tests that using these technologies. For example, we have near the UT Arlington area, we have constructed the pedestrian here pavement and have old pavement here. So we can easily compare that. We don't know exactly what the volume crack, but based on our laboratory testing, it's pretty accurate. And so you can compare these two. And so if you look at the RACM result, you can see the damage volume increase in old pavement while the new pavement is less. But probably they have a dry shrinkage, a small big crack here too. Our 3D tomography is not really helpful to find the crack, but you can see the anticipate the thickness. So this red color is indicate the thickness of the pavement. Same thing, we repeat many locations here. We test the parking lot, and you can get all the data here. And also we did for bridge deck here, so that we same tests here, and then we got all the data here. And like I said, we developed a web-based platform and mobile app platform as well, so that once you click the button, this location, you can see the Monday testing, Tuesday testing. Also, you can see all the photo and data, and then our RACM data. So you can, many people can access the data anytime. And also, if you test every day or monthly, you can always track all the information, so we can discuss how this is an infrastructure damage, so that we can always communicate with other stakeholders as well. So these are just examples, and then this is actual data we developed here. So I already explained this bridge deck, application field testing, and parking lot field testing, and payment field testing. So all the data is already saved here. So anyway, so the conclusion of this CTEDD project here, we can able to access all these. We can able to access all the in the field test area, and we can able to extract all the crack. But this technology can transfer the other area, such as we developed recently after the CTEDD project, we developed some mobile scanning system, so we can do some runway payments, because we wanted to investigate, and we want to help the stakeholder to how much damage here, because they don't want, again, they don't want to underestimate or overestimate, so they lost $1 billion. So we help this, currently we use this technology, we help this other stakeholder. And then we also similar project, but we use robotic, the scanning pipe system, because we have a, like Fortress, we have an entire, like a large complicated the pipeline. This robotic system is non-contact fashion, so we can investigate other area as well. Or we have manual bridge scanning system. So this is the previous data from DOT project. So we identify the internal damage, corrosion stage, surface crack as well, which is the internal crack is very unique, because other technology, GPR or other image processing cannot detect the internal damage like this. Anyway, so this is the future our work that 4 or 5 years ago we initiate this this augmented reality called the AR technology, that because although we have a web-based system, still we have questioned how the repair team or engineering team, they want to identify exact location, they communicate in the field area or office. So how we can do, so we adopt this augmented reality system, so we record all the 3D system, and then all the complicated ND technology into our system, so everybody can access in office, or they can go there. So engineer team go there, they find the exact location where the defect, how we can core it, because they also need the coring, which is like a blood testing in the human body. You want a coring, and then you can see that here. So this is really helpful for communicating with other stakeholder or team. So communicate. So it'll be, hopefully this technology will be next one. Anyway, so thank you so much about today's attending, and I appreciate the technology, the CTEDD.
Sure, thank you, Dr. Ham, for the explanation and your great project. We have a question and answer box on the webinar. If you can check, maybe it'll be at the bottom or at the top of your screen. So if you have any questions about any of the things that Dr. Ham mentioned, feel free to type them up, and he will be more than happy to answer them. We're just going to wait a bit if anyone has any questions.
Mm-hmm.
We haven't received any questions yet. Nobody has any questions? No. We'll wait for a little bit more. Also, in the meantime, if we go, this is the CTEDD's, you can actually contact us on here, on this, you can call us on here, you can email us. Okay, we have a question. When is this technology going to be available for the DOTs?
Right now.
Oh.
Yeah, we are already involved the several like CD and so it's available now. We can deploy this technology.
Great.
Thank you.
And what's the process for, I guess, implementing this technology at the DOT level?
So DOT level, that we have to discuss, first of all, what kind of deterioration they're looking for. For example, the current project I involved is like they want to find the vertical crack and the lamination, which is horizontal crack, and any void area. Then we can use we mix with the RACM, and then we have some advanced impact ecosystem. So we evaluate, and also we use the GPR system to indirectly see something. We also develop some advanced post-processing of GPR systems, so we can anticipate the corrosion level. But more important is that we can find the crack, and I showed that already. That's the last page that I showed the 3 map, which is finding delamination, which is actually previous DOT project that I helped the Nebraska, Illinois, and Virginia. I mean, that's a good question. So I need to discuss with the stakeholder, first of all, what they need, and then another project I involved is there's new material for pavement. So they want to know initial any micro crack, or sometimes they contract to cast the concrete, but lots of maybe there's a weak foundation, they're void. So they want to check the kind of void or crack. So that case, we can also help. I helped with this RACM technology and 3D tomography. Yeah.
And then it says, is Dr. Suyun the contact of the DOT? If they want to contact you, then yeah. So the email address that we have provided here, s.ham@uta.edu, we can definitely contact him for this specific project.
Yes. Yeah. And anytime I can meet you in person, or phone call, or email me, then I can contact you. Yeah, or we can make it. All right.
Okay.
Thank you. Yeah, thank you.
All right. Any other comments, questions about the project? So we have put up his email address. So if you have any questions, you can definitely email him and get in contact with him about the technology and the research. And if you want to find out anything about other CTEDD projects, we have all our email addresses here. I can go back to the last page so that maybe you can see that contact information. So yeah, you can call us, you can email us, and we are cted.uta.edu, and that's where we have all these projects uploaded. Even this webinar is going to go there, so even if by any chance you'd like to share this with anyone, you can definitely do that. We're going to upload it there soon. And all other projects and activities can be accessed there. So thank you so much for attending this webinar. We'll keep you posted on all upcoming events and webinars. And again, if you have any questions, please don't hesitate to contact us. Thank you.
Thank you.
Thank you, Doctor.